So this lecture is on block diagram simplification, and the first thing we're going to do is take a look at the learning objectives. So let's have a look at the learning objectives. Well, in a feedback control, one of the main things is that we could have a complicated arrangement of block diagrams which we need to analyze. And if we just look at the block diagrams as they are, they're really impossible to analyze. So we have to have a way of simplifying them down to a single block. Once you've got a single block, we can then apply quite a number of analysis techniques to a single block, because as a single block, they're single polynomials which are mathematically analyzable. So in this lecture, we've become familiar with what block diagrams look like and how to use formula to simplify the block diagrams. We'll also use a signal flow to simplify the block diagrams as well. So it's like two techniques here. And then when we looked at that, then we're able to simplify any complex block diagram down to a single block. Now this is a key skill that you'll need throughout the course, so it's well worth concentrating on. Once you've got this, then everything becomes very straightforward. So this lecture is on block diagram simplification. One of the key skills that we need in designing flight control systems is the ability to take a complex block diagram and simplify it down to a single block. Once you've got it as a single block, the analysis process becomes much easier. Many flight control systems have fairly complicated flight controls and complicated block diagrams. This is a little example of a space shuttle flight control system, which is looking at the landing control systems. So here is the block diagram, and notice that it's got multiple feedback loops in. So this is what can make our block diagrams a little bit more tricky to analyze. We're actually measuring acceleration of the aircraft here and feeding it back. We're measuring the pitch rate of the aircraft and feeding it back. I'm also measuring the pitch angle. So there's like 3 feedback loops here, and what we need to be able to do is simplify this whole thing down to a single block to analyze it, which is where block diagram simplification comes in. Here's another example. This is an altitude hold block diagram of a 747. It's got a pitch rate sensor here, pitch angle sensor here, and an altitude sensor around here. So it's got 3 control loops, and again we'd have to simplify this down to a single block. Another example, heading hold autopilot. This has got the heading feeding in here. It's got the actual heading of the aircraft coming out here, and again we can see we end up with quite complicated block diagrams to analyze. Finally, here is a more complicated autopilot design using heading hold. This has got 2 inputs into the control system. It's got the elevator and the engines, and we've got a forward speed control and an altitude control running simultaneously, and lots of feedback loops in here, again, which we'd have to be able to analyze to simplify and do detailed analysis on. So obviously we can't start with these complicated systems. We have to start with something simple and straightforward, and fortunately block diagram simplification can be broken down into a series of quite simple steps which we can all do. And it really starts at this point here. There's 2 basic features that we must understand. One is a summing junction. So this is where some signals come in and some signals come out. So in this particular case, I've got X3 coming out, I've got A1X1 going in, A2X2 coming in, and a 5 coming in. But this, because it's got a minus sign here, it's coming as -5. So if you've got a summing junction, things coming in, coming out. The things going out are equal to the things going in. So that's a nice simple one, but we'll need this repeatedly. And the second important one is if we've got x1 coming in and a1 in the box, then the output is this times this. So the output from a box is what's in the box times the input. So those are the two basic building blocks for block diagram simplification. So just coming back to this one, the output is given by plus this, and minus that. If we had a more complicated arrangement, we could have an infinite number or a large number of loops here, then the output is just equal to the sum of the inputs. Now, in block diagram simplification, the systems are very often described originally by differential equations, which we convert into transfer functions. Now, we'll be looking at transfer functions in the next lecture, but we'll just assume now that there's something called a transfer function, and this is always characterized by a letter G for transfer functions. It's like a sort of universal symbol for transfer functions. And so we have an output which is usually called Y as well. They like Y as the output and U as the input. So this is a bit of a standard format now for feedback control systems. Output Y, input G of S, input U of S. And so in the next examples, we're going to look at replacing letters with transfer function symbols, GS, which we might have as G1 of S, G2 of S, G3 of S, as we build up the system complexity. So here we have a transfer function G1 of S, another one G2 of S, and another one G3 of S. And these now are in series, which we call cascade form. So we can say that this signal here is this one times that one. And this signal here is this one times that one. And this signal here is that one times that one. So net effect is that we can simplify this down to one block where the output from the block, there's the output here, here's the input here, and this is simply what goes in here is just this times this times this. So we just multiply the three together and that goes in the block. Then this is the equivalent now simplified transfer function. If we have two transfer functions in parallel, then what we've got now is this signal here adds on to this signal here to give this here. So what we've got is in parallel, they add up. So in parallel form, if we've got a number of transfer functions coming in, then it would be simply we'd add this to this to this. So in parallel form, they add up, whereas in series form, they multiply together. So this gives us a good starting off point now for thinking about block diagram simplification. And there's one further one that's important, which is the feedback form. And this one's a bit more complicated because we've got a signal coming down here, which feeds up here, and then we've got a signal feeding in this way. So this time we've got two blocks and a summing junction. So this one will need a little bit more analysis on it to actually be able to do it. So if we do the analysis on this one, it comes out, the transfer function comes out as G of S over 1, and depends on we've got plus or minus here, plus or minus this times this. So this is the simplification of this one. And I'll do a little example to show you how that works now. Right, this little talk is going to be on block diagram simplification. And in order to do this, we need two main little skills. Let me show you. this is a semi-junction, and we could think of this as being, say, P, Q and R, and we can simplify, we can form an equation from this really, which is that R is plus P minus Q. So R is P minus Q. That's a key skill that we need to have. And the second one is this one here. If this is A and this is B and that is C, then from this one we can say that C is B times A. So C equals BA. And in these sort of feedback systems, BA is the same as AB. Because there's essentially like scalar type things. So 1 times 2 is the same as 2 times 1. And these are the two key skills now that we're going to repeatedly deploy to do our block diagram simplifications with. So I'm just going to put those up here so we've got them on board all the time. So here we go. These could have different signs on, but it just depends on what system you've got. But usually they're plus and minus. So that's P and Q, and R is P minus Q, and this is A, B and C, and C equals AB. So here's our two little key pointers. And now we can do some block diagram simplifications. So let's have a look. So we've got 3 boxes like this, and we put A, B and C in the boxes, and let's say this is X, Y, Z and W. So what I want to do now is replace this with one box with X coming in. You should have a bit of arrows on really. Get the arrows on. X coming in and W coming out. So we can say now that Y is AX. So we've got Y is equal to A times X. Using our trick here, we can say that Z is BY. So Z equals BY. But we know now that Y is AX. So Z is equal to actually BAX. We also know that W is CZ. So W equals CZ. But Z is BY, is BAX, so W is equal to C BAX. And because CBA, because it's scalar like 1 times 2 times 3 is the same as 3 times 2 times 1, then we can say that W is equal to A BC times X. So you can see this is as simple as ABC. And this is our basic idea now behind, starting off point behind doing block diagram simplification. So let's have a look at some slightly different examples. Let's maybe move a block here. So we could have maybe block C here. We do that on a plus and a plus, and that can be, this can be Z, and that can be W again. So this is going this way this time. So this time we've got scan 3 blocks, ABC, but this is not going to be as simple as ABC. So the first thing we have to do now is, when we're looking at these, it's always best to do ones in series first.
So the A and the B could be replaced by multiplying these two together. So we could have a simplification now of AB. We know that AB is the same as AB. So therefore we could rub these out now and merge them into one box with AB in. Now, if we've got two in parallel, what's happening now is we've got that W now is equal to this signal here, which is going to be ABX, plus this signal here, which is CX. And then we can take X out as a common factor. So W is equal to AB plus C times X. So if we want to simplify this now, we've got a relationship now between X and W, and so this is actually equal to AB plus C. AB plus C. So this very obvious really. Get the first two, AB, add them to, so it's multiplied because they're in series, in parallel, added up. So AB gets added to the C. AB gets added to the C. Now, in some situations, we might have a bit of feedback in. This is what we've had up so far is called feed forward. In feedback control systems, if it's going this way, it's forward. If it's coming back, it's called feedback. So if we have, say, A here, another sending junction here now, and this time we've got some feedback coming in here. Let's put the feedback through B. Let's have a look how we can do this one. So we can call this, say, call this X, and we'll call that Y, shall we? X and Y. So this time, it's similar, but not quite the same. Now, one of the good tricks to do here is to follow your signals around the block diagram to make life easy for yourself. And so this signal here, we know is Y, because this is Y here, and this signal here will be given by this is this times this. This is going to be BY. So this signal here now is going to be X minus BY. So that signal there is X minus BY. But we know now that this is this times this. So this will give us the equation now for describing what's going on. So now I'm going to get that Y equals A times this. It's going to be A into X minus BY. Now, this is a bit more complicated because I've got Y on this side and Y on this side. So I've got to expand this out, collect the Y's together and rearrange it as a single block with X coming in and Y coming out. So I'll need to write this as Y equals something times X. So again, mathematically it's quite simple. It's A times X minus A BY. Collect up the Y's, so we're going to get 1 plus AB times Y equals AX, and then Y equals A over 1 plus AB times X. So in this box here, now we have A over 1 plus AB. So in these feedback configurations, they do tend to get a little bit more complicated, and one of the ways to do these, which I find very helpful, is start off at this point here, follow the signals round, get an equation for the last box. So you say that output is the last box times the input here, and then that will give you an equation. Then rearrange the equation then to get your block diagram.
So, having done that, we've now got a number of block diagram reduction techniques which are worth bearing in mind. If we've got two transfer functions G1, G2, then we simply multiply them together. If the two are in parallel, we add them together. So there's a couple of simple rules. It could be that we might want to move a summing junction for some reason in our block diagram to make it easier to simplify. So if we look at the signal coming out here, is equal to G times the input signal minus G times this signal here. So we could simplify that, or could move the summing junction onto this side, because the signal coming through here is the same as that signal going through there, and the signal coming round this way is now the same as the signal coming round that way. So by adding in an extra transfer function with G down here, we can simplify this to this, or maybe not simplify it, almost complicate it. But the advantage might be we might want to move this summing junction to here for some reason. So this is an extra moving summing points trick that we can deploy sometimes in block diagram simplification. So looking at some more of these tricks here, if we've got a summing junction after the block diagram, we could move it in front, and again what we'd have to do is the signal going through there is G times the input signal minus this signal here. So that's going to give us the G signal that way. That's the same as that, and then this one here has got to give us a signal of just 1. So if we've got 1 over G times G, that'll give us the 1. So that'll give us the 1 going that way and the G going that way. If we've got a block diagram like this, we've got this coming back that way, so that's just the main signal going back that way, and G going through there. So that signal going through there still gives us this signal. This signal coming around here has to be equivalent to this. So the only way you can do that is by multiplying, because it's got multiplied by G now, multiplied by 1 over G, it'll go back to the normal signal. So here's another one. And last one is if we've got some signal coming around there, and then that signal is G, and that's G. So that's going to be G, and this is going to be G. If we've got feedback block diagrams, then if we've got a G and an H here, we can simplify it by this. We just had to look at that a minute ago. And if H was 1, it simplifies to this. If we've got two summing junctions, we can interchange these willy-nilly, and it gives us the same effect. So these are the main tricks that we might want to deploy in doing some block diagram simplification, and they're all worth bearing in mind. And here's a little table of them here. There's 2 pages of these which just sort of summarize those basic things. So we've got the series, the parallel, the feedback. We've got moving junctions in here, so these are the moving junction ones, and there's a few more moving junction ones there as well. So as a general technique for simplifying block diagrams, combine all cascade. You can do these in a certain sequence, so it'll make it easier. Combine the cascade ones, that's the ones in series first, then do the ones in parallel, then any inner feedback loops, get rid of those, and then if you've got any summing points to the left of takeoff points or to the right, you can move those around, and then repeat then steps 1 to 4. Repeat this process as you move. Start at the center of your block diagram and move outwards. So you start at the middle of the block diagram and then move outwards and get to the edges of the block diagram and repeatedly use this method. Looks a bit complicated, but when you actually come to do it, it isn't too bad at all. So we're now going to look at some examples, and you can have a go at some examples. Now here are some further examples for you to have a go at. These are 4 worked examples, and what you can do here is, here's the first example. Simplify this block diagram here. It's actually got the solutions here, so on the remaining few pages there are the solutions, and you can have a go at working these out. So my recommendation is have a go now doing this yourself, but you've actually got the answer here. So once you've had a go, then you might want to know how to do it. So the first thing you do, start at the middle of it. So take those 2 and simplify them down to this. So then this replaces this. Then take these 2 and replace them with this. So then you've now replaced those. So that's the next thing to do then, is to take this part here and reduce that one down. So that's what we've done here, taken those 2, reduce this one down, and then so then that gives us this. We can then multiply that by that using the cascade one to give us this, and then we can take this one and simplify that then down to the final answer. Here's another one to have a go at. This one's a bit more complicated. It's got a feedback loop around that way and a feedback loop around this way. So this one is quite a bit more tricky than the previous one. And one of the problems we've got here is we haven't got any distinct feedback loops which aren't affected by any other loop. So this loop here is affecting this loop here. So what we're going to have to do is get this loop here to be clear of this one here. So what we've done is going to move this semi-junction over here. So in order to do that, because this has got a G1 in here, if we move that to there, this box now will become H2 over G1. So once you've got it into this form now, so this is one of those where you've got to move a junction. So we're moving this over to here. It can go into any one of the, but better to go here really where they put to here. And because you've got a G1 there, this will have to be H2 over G1. So now what you got is you've now got this part here which we'll simplify. So that'll give us one loop. Then when we've done that, we could then simplify this loop here. And then we could simplify that loop there. So there'd be like 4 stages to this. First stage, move this to there. Second, simplify this loop here. Then simplify that loop there. And then finally simplify that loop there. So looking at that one, so the first thing to do would be to simplify this one. Then we could simplify this loop to this one. And then we could simplify this loop to this one to give us our final solution. So that is just a recap really. This is a slightly more complicated one again, where we've got a block diagram coming down that way, another one this way. So we can see on this one, got the same problem really, got a loop here and a loop here which interact. So what we need to do is break the loop. So we're going to move now this loop here onto that side. So this is going to move onto the other side of G1 of so we're going to move this. We're actually going to move this to there. So to move this to there, we're going to have to, we've got a G4 here, so this is going to be H2 over G4. So by moving this one onto here, we can start now to, because the loops aren't interacting now, we can simplify them. So we can now simplify that loop there, so one loop. then we could simplify this loop to one loop, and then we could simplify that loop. So the secret with this one was to notice if we could move this to here, then we could make it a lot easier for ourselves. And the technique for that is, because we're moving onto this side, then this signal here would have to be, if we put it on this side, gets multiplied by G4, so therefore it would have to be divided by G4 here. So when we've done that, we've then got the ability to simplify that loop, then simplify this loop, then simplify that loop. So look at that. This was the process. We simplify that inner loop, we simplify this loop first, that one there, which gives us this transfer function here. Then we simplify this loop here, which gives us that transfer function there, and then we simplify this one, which gives us that transfer function there. So these are quite complex examples, but ones that do highlight how it can be done. Here's a final example. We've got 3 feedback control loops, and because they're all on a plus here, and these are in cascade here, we can just put one semi-junction instead, and then we can, because these now are in parallel, parallel means you can add up, so it means we can simplify that to adding these 3 together. Then that goes around these 2 transfer functions here, around these 2 here. So that gives us this to simplify. So we could use that standard block diagram technique to simplify those, and then multiply the solution by G1. And then that gives us our final answer. Here's I think it is the final one. This is a typical one might do. This one we'd have to simplify this loop here first, and then simplify that loop there second. So we would take this loop here, and then simplify the second. So if we simplified this loop here, it would come down to this, and then we could simplify this one here. This is putting some letters now into the transfer function, and then we could simplify that to the next stage. So that's given you some experience of looking at block diagram simplification. I'm now going to look at some more examples on the whiteboard for you to have a go at, and I'll set some examples on the whiteboard for you to have a little practice at, and then I'll provide the solutions to them on the next video. So good luck with your block diagram simplification. It's the key to being able to do flight control. It's a really good skill, and I'd recommend that you practice it as much as you can, because once you've got that one under your belt, everything else will be pretty straightforward.
So here's another little example for us to have a look at. This time it's got 2 feedback control loops in, and we've got the letters A, B, C, D and E. Now in order to do this one, we will need to do when block diagram simplification, do the inner part first and move outwards. So we could look at the ABC one first of all. So we could think of this as A, B and C. So we're going to look at the inner loop ABC first. So nice C. That's really good there. And we need to have some labels on this, so I've got a W and an X. And this is quite similar to the one we just did a minute ago. So the best thing to do with these is to follow the signal round. So that is going to be X, and this signal here is going to be CX, because we know that this signal is that times that. And therefore this signal here is W minus CX. And then we can say that X is this times this times this. So get the equation, which says that X is A times B W minus CX. That's saying that this signal is that, times that, times that, using our standard signal through a block. We can then say that X is equal to ABW minus ABC times X. So we've got some X's on this side and some X's on that side. So we bring these X's over. Remember, as they come over, the sign changes from a minus to a plus. So we get that this is the same as 1 plus ABC times X is ABW. And the last thing to do is to move this term onto that side, but just as we go over, it goes underneath. Nice trick. So we get that X is equal to AB over 1 plus ABC times W. So what we've been able to do now is simplify this block down to this. So that means now that we can remove this part here and replace it with AB over 1 plus ABC times that. So this is the trick now with block diagram simplification. We take the inner loop and replace it with a single term, making it simpler, block diagram simplification. So next we have to do now is do this one now to get the final block. So we don't need this anymore, so we can rub this out. And now, again, I'd recommend the same technique. So this signal here is Y, and this signal here is E times Y. And therefore this signal here now is plus B minus EY. And then we can say that this is this times this times this to get our little equation. Because we can say this is a single block here, because that times that can be simplified. So if like we could simplify that by moving the D into there and then doing away with that. And then we can say that this is this times this. So get the Y equals ABD into V minus EY divided by 1 plus ABC. So this now Y is this times this. So this is now needs rearranging. So the first thing to do is move this up. So I get 1 plus ABC times Y equals ABD times V minus my B's going this, ABD E times Y. ABD E times Y. Now what I can do now is I've got some Y terms on this side, some Y terms on this side, so collect them all together. So I get 1 plus ABC plus ABDE times Y equals ABD times V. Final trick, with all this underneath there, so you get that Y equals ABD over 1 plus ABC plus ABD times E, and that is times V. So what we've done then is taken our big complex block diagram and simplified it down to this block diagram here. So here's our next example. Now this one is a little bit more devious because we've actually got a feedback loop here, which is fine, but can't simplify this because it's got a takeoff from the middle of the block into here. So this one now will need a modification before we can directly apply block diagram simplification techniques. And what we like to do is move this one here over here to get rid of this loop here. Then we can apply then our standard feedback configurations. So we're going to have to change this. Now, bear in mind the signal going into here is X. So, isn't that hard to do? Take this away here and put an extra block in there and feed round to there. Now the question is, what do we put in this block to maintain this signal as X? Well, if we look at the diagram, we know that Y is dx. So Y equals dx. And what we want is a signal for X here. So we could rearrange this now as X equals 1 over d times Y. So if this signal here is Y, but we want this to be X, we could make that 1 over d there. And so this is now the block diagram in a format that allows it to be simplified. So what we've done is we've taken this loop here, replaced it with that one there, and then worked out what that is using just the knowledge of this signal here. So this now gives us a block diagram, which is now relatively easy to simplify. And the way we can do it, start off with this inner loop here. So we've got this system here now. We've got a B and a D and a unity feedback. So there's our little loop there, and we could call that, say, X. We're going to call it X, and let's call it P and Y. So again, to simplify this one now, we could use our thinking ball head forward. So this signal here, in this particular case, is Y, and this signal here is going to be P minus Y, because of the plus and minus. We can then say that Y, this here is this times this, so it's going to be B times D times P minus Y. So this is this times this times this. We can rearrange this as Y equals B dP minus B dy, and collect the Y's together. So get that 1 plus BD times Y equals B dP, or that Y is BD over 1 plus BD times P. So what that allows us to do is to take now this part here, which is this part here, and replace it with this. So we can rub this out now and replace this with a single block, which is now BD over 1 plus BD. So there's our first simplification done. Now we have to move on to our second simplification. So this one, we know now that the signal here will be V minus, so this is Y, so the signal coming out here will be C over D times Y, because that turns out to be C over D multiplied by Y. So this is going to be V minus C over D times Y. And that's going to multiply then by A BD over 1 plus BD. And that's going to equal to Y. So we've got V minus C over D times Y. So that's a term going down there. That times that is equal to this. This now gives us our equation. Now, one thing to watch out for, we're never very strong with fractions, so I'd recommend that we rewrite this as VD minus CY over D. By taking D now as a common factor out in this, and then that multiplies by ABD over 1 plus BD times y. This will make our algebra much simpler. So now that is equal to y. Equal to y. So we can now take d into 1 plus bd onto the top. So we'll get that vd minus cy times ABD is equal to d into 1 plus BD times y. So I've taken d, 1 plus BD, moved it up there, and I multiplied this term by that one. So I've now got ABD squared this time, ABD squared times v, that's ABD times d is d squared times v, and that's equal to, collecting the y, so I'm going to get onto one side now, I've got d plus a d squared, that's the d plus, bd squared, bd squared, and I've also got an a, b, c, d here, so it's plus a, b, c, d multiplied by y. So that's giving my d times ab times d, that's giving my abd squared, then I've multiplied by the b, then I've got a, b, c, d times y, so that's become a, b, c, d, and I've got a d plus a bd squared. And then I can just simply move this term underneath here to give me that y will be given by a, b, d squared divided by d plus bd squared plus a, b, c, d times v. Now, if we look at this, we'll notice that we've got a d everywhere. So that means we could cancel a d. So I could lose that d, make that then become a 1, that would become a 1, and that would disappear. And then that is my final block diagram. So there's a very complicated one, which needed a bit of movement and a bit of extra manipulation. And then that is your final block diagram simplification of what we had. So I'm going to do some examples next for you to have a little go at on the board, and you can have a little go at doing these, and I will supply little solutions for you to look at later on. Thanks. Right, so here on block diagram simplification, there's 3 examples for you to have a go at. This one is straightforward. This one's also very straightforward. This one's a little bit more tricky because of the fact that this is going into a middle of a loop here, so I have to think about that one a little bit more. But here's 3 little examples to have a go at and see if you can do them, and I'll provide you with some little answers later on. Right, so here's our 3 examples. We can have a quick go through these now. You should have a go at these, at doing these. So on the first one, the signal coming round here is y, so that's going to be v minus y. And we said that y is a into v minus y. This is that times that. And rearrange this as y plus ay equals av. Take y as a common factor, it's going to be 1 plus a times y equals av, or that y is a over 1 plus a times v. So it's a over 1 plus a. Second one, on this one, we've got a feed forward section here. So this part here could now be simplified, and because they're in parallel, we can simplify that as A plus B. So we could get rid of that and just have this as A plus B in there. So that'd be our first thing to do. And then, very similar then to this, in a different size, we've got an A plus B there and a C there. So it's going to be, that signal there is going to be V minus CY, no, sorry, V minus CY. So we're going to have V minus CY into A plus B is equal to Y. I'm going to say that this is that times that. Then we can rearrange this as A plus B times V minus A plus B times CY equals Y. Then we can collect the Y terms together. So we get A plus B times V is 1 plus A plus B times C times Y. And then we can simply rewrite that as Y equals. So we get the Y equals A plus B over 1 plus AC plus BC times B. And then that's this block diagram simplifies down to this one. So just got one more to do. I'm running out of space here now. So what I'm going to do, I'm just going to get rid of our two previous examples. And have I got this one? Right, so with this example, we've got slightly more awkward than the other ones because we've got a feedback loop around here, but a feed forward loop coming in the middle of the loop. So we can't we can't simplify this one because of this one. So in this particular case, I've redrawn it over here for us. It might be a better approach might be to follow the signals around the system. So this signal here is Y, and this one here is CY, because that comes out. And this signal here is V minus CY, and this signal here is A into V minus CY, because this one is that times that. This one here is just D times V. Now there are a plus and a plus here. This signal here now would be what we get if we add these together. So it would be A V minus CY plus dV. So the signal there now is this one plus this one. We can then say that this is this times this. So we get an equation out for Y. Y is B into A V minus CY plus dV. So we can now look at rearranging this now. So you can get if we expand it out first, Y is BAC, so it's B minus BACY, BACY, ABV plus ABV plus BDV. Just check that. We've got BAV, ABV, BAC on a minus times a Y, and then B times a D times a V. So we can now connect these together So you get 1 plus ABC times y equals AB plus BD times V. And we can move this underneath to give us that y equals A plus B times D over 1 plus ABC times B. So this one is a little bit more complicated, but a good way of solving them is to start off over here, follow the signals round to work out the last signal to the last box, and then say the output from the system is the last box times the last signal. That then gives you this equation. It's just a matter of rearranging to get your answer. So that is my preferred solution with a more complicated block diagram. Thanks.
Right, so we now got to our learning objectives review. So what we've done in the lecture is we've become familiar with block diagram simplification. We then used formula to simplify block diagrams. You've got an idea now what those formulas are. There's about 3 main ones. You can also use signal flow to simplify block diagrams. Now this will appear in the sort of stand-up lecture I'm going to do after this lecture. And then when you've done those things, you're now able to simplify complex block diagrams down to a single block. So to check yourself out now, we're going to have a little knowledge assessment. So here's a simple block diagram. See if you can simplify this down to a single block, and here's the answer here. So there's your first little test. See if you can do that. Second test, so it's got 3 blocks in this down, and so it's a little bit more to do. There's 2 in forward loop here, and there's 1 in feedback loop here, and here again is the answer. And finally, here's 4 blocks. So there's a 4-block system, and this is now the answer. You can see as the blocks get more complicated, the mathematics gets more complicated as well. But don't get put off by that. So last thing is to have a bit of retrospective reflection. When you've done your lecture on block diagrams and you've done the MATLAB block diagram workshop, then have a think of the advantages and disadvantages of either using MATLAB to do it, or doing it by hand, or doing it using some of the rules. One of the things to bear in mind, which I think is important, is if you've got multiple feedback loops, just realize that you have to start off in the middle and then go to out. If you start on the outer and try and move in, it won't work. So have a little go at this problem and tackle it from 2 points of view. Simplify this first and then simplify that, or simplify this first and then simplify that, and you find the second approach doesn't work. So when you've got multiple feedback loops, you've got to start on the inner loop first and work out. So see if you can just realize that, and then you'll become expert at block diagram reduction.